If we did what we just did, which is use straight constant functions and rectangles, so constants, then we fit linear functions on each interval. What might be something to try next if I want to get even better performance? Second order, quadratics. Taylor polynomials, they are not just for fun. Quadratics. If there's anything from calculus that transitions to numerical methods, it's this idea of as we increase order of polynomials, constants have 0 order, linear is first order. Hey, if I go to quadratics, something's going to get more accurate. I'm going to have less error somehow. And you'll see that as a theme through various kinds of numerical methods. And we actually saw that with the bisection of secant. Bisection, we assumed things were just constant. Secant, we said, oh, what if it's a straight line between it? And then when we looked at the built-in MATLAB functions, they said, hey, what if it's a quadratic? It's the same kind of theme here. You often get increased performance, increased accuracy, if you're willing to model your function as something a little more sophisticated than the thing before, linear and constant, for this case here. So here's what it looks like. We have our function. Now this gets a little bit more complicated because if I have 2 points, I can fit a line. But to fit a quadratic, I need 3 points. So what we see here, you can probably see it better if you have it on your own screen, is the dotted line is the real function. But it's possible to fit uniquely, to get an interpolant, as we saw back before reading week, an interpolant on 3 points that's quadratic. And so what we do here is we literally fit, not even fit, we interpolate a quadratic through those 3 data points, those 3 measurements, and then we do one through the next 3. We're going to keep delta x meaning what it meant before. Delta x is the distance between any 2 points. But what we're going to do is find the area on panels which are 2 delta x wide. And then on the next one, which is 2 delta x wide. And there's going to be a little bit of an asterisk that we have to put in here. I have to have an even number of intervals to do this, right? You might ask, hey, what if I don't have an even number of intervals? What we usually do is do all the even ones up to the last one, and then maybe use the trapezoidal rule on the last one. That's the usual hack around if you don't have an even number. But otherwise, the principle is exactly the same. I'm going to find the area under the quadratic, and it's going to have something to do with the width, which is 2 delta x. That's basically it. So we can go through the math. Most people don't find it that enlightening, though, so I've taken the shortcut. Surprisingly, you might think, hey, quadratics are really, really complicated. What's the area underneath it through those 3 function values going to be? It turns out it's really simple. You take 1 of your fxi's, you take 4 of the I plus 1s, and 1 of the I plus 2s. This is an average height. It's a weighted average, so it's a little more sophisticated than what we had before. But if we compare it with what you saw on the trapezoidal rule, it has exactly the same kind of shape. The trapezoidal rule was that over 2 times delta x. This one is 1, 4, and 1, which adds up to 6. So it's 6 heights. And then we divide by 6, so we get a height when we're done. And then we multiply by the width of the interval there, which is 2 delta x's. So you'll see it written this way, or you'll sometimes see it written with some of the cancellations happening, the 2 and the 6 here. We can end up with 1/3 all this stuff times 1 delta x. It doesn't matter in practice. I just like seeing it this way because it ties it back into the other integral techniques. So that's nice. Again, it would be nice to maybe derive that, but it takes about a page, so we'll skip that. But if you believe that this falls in the same pattern as the trapezoidal and left-hand rules, which it does, we should be able to implement it fairly easily. So we're going to make a new function, and we're going to call it simp.m. And we're going to do exactly what we just did with the last 2 examples. We're going to code it, and then we're going to run it and compare. So we'll make a new file called simp.m. We'll fix the file name. Where'd it go? Simp. And the only thing we need now is yet another x value. We need xi plus 2. And so that'll be 1 more delta x. And then we just have to be careful about this. I'm going to make it look, again, exactly like the math that we saw on the page. 4 of the middle one plus 1 more of the last one. And that looks pretty good. 1/6 f of xi plus 4 f of xi plus 1s plus an f of xi, times 2 delta x's. That's the fundamentals. Let's try it out and see how it works. So we'll go back to our main script. We'll make an I3, which has exactly the same form, but now we're going to use Simpson's rule on the integral of f from 0 to L using n intervals. We'll go back to 100 intervals for a second. And this is going to be hard to read. So I'm just going to call it L. We know what L is, left-hand rule. T for trapezoidal rule, error. And whoops, that's not what I'm going to do. And we'll call the last one S. All right. And we'll do exactly the same thing. Will this work? Let me try this. No, it's not going to work. All right. If you put a dot, dot, dot at the end of a line, then MATLAB will let you continue a line into the next thing. We're going to do that just so it's a little easier to read. So our print statement is going to print how many intervals, and then the error in the left hand, error in the trapezoidal, error in Simpson's rule. And we're going to run it. And it runs. Clear the screen here so we get a fresh slate. Oh, crap. What we're getting out of Simpson's rule doesn't look like the exact value. How do they seem to be related, though? If you had to multiply one to get the other, what would you multiply by? 2. This is not a coincidence. This is actually the most common mistake people make on their tests when we ask them to implement Simpson's rule. So notice this formula is totally fine. This formula is beautiful. The problem is, how do we implement it? If you look at how we break this up, I grab the first 2 intervals and I find the area on that. Then I throw them all away. And then I start from the 3rd to the 4th, 3rd and 4th. So I'm going to count not by 1s, which is what trapezoidal do. Count by intervals by 1s. Here I'm going to group them and count by 2 interval sets, because I'm doing 2 delta x's every time. So fortunately in MATLAB it's a super easy fix. I'm going to count to the end, but I'm going to count by 2s. So just make sure that that comes in there. If I don't, I get twice the area. So step count by 2s. And notice I'm going to get x1, x2, x3. And then the next time I'll have x3, x4, x5. So we won't have overlapping sets. This is perfect. We'll go back to our script. We'll run it again. And oh my gosh, it's awesome. There are very, very few clear wins that are as clear as this. Which method's best? All together. Simpsons. Thank you. And we're going to find out it's even ridiculous. It's just, there's no comparison. All right. I'm going to, in fact, I'm going to have to add more digits to show the error at all for Simpson's rule. So let's run that again. And then we'll try doubling the number of intervals. And running. And 400. Run. And 800. Not only is it better for a fixed number of intervals, as we are willing to do more work, as we're willing to spend more time calculating more intervals in our calculations, left-hand rule, double the work, half the error. Trapezoidal rule, double the work, 1/4 the error. You might have had various guesses about what happened in Simpson's rule, but what do you get as a factor? It's easiest to see in this last step. What do you get as a factor if you double the work? 1/16, 2 to the power 4. Yeah, so if I want to get 1/10 the error, reduce the error by 1 order of magnitude, which is usually a big thing, I only have to do twice as much work. It's very rare to get that kind of payback on anything in computers, quite frankly. But that's exactly it. As you move down here, doubling the work gives you 1/16 the error, which is great. We can get very, very, very accurate calculations of areas and integrals with Simpson's rule. And it's, again, unambiguously better than either the left-hand or trapezoidal rule. There's just no comparison. It's better on a given number, and it's better as you do more work. I can't express how much I love Simpson's rule, quite frankly, as a tool for what it does. The one thing I just want to reinforce is, again, how much better this would be. So Simpson's rule with 100 intervals, here it was, had an error of 0.0000004, like 4 times 10 to the minus 8. To get the left-hand rule down to that, well, every time I do 10 times as much work for left-hand rule, I'll get 1/10 the error. If I double it, I get half the error. I do 10 times as much work, I'll get 1/10 the error. I'm off by 10 to the power of 6. So I would actually have to do 1 million times more work with the left-hand rule. I'll actually just try that quickly. If I use 1 million intervals, am I going to get to the right ballpark? So 1e6, not 600, 1e6, which is 10 to the power 6. Notice now it's taking some time. We're actually spending some real, honest-to-God computer time here. And, wow, longer than I expected, honestly. But that's what it would take to get the left-hand rule to perform as well as Simpson's rule just basically did with a standard 100 steps. So that's the real visceral payoff when you see how long it takes to run in other kinds of scenarios. Trapezoidal rule, you could do it with less. But, oh crap, I didn't even get far enough. 1, 2, 3, 4, 5. In fact, I'd need another 100 times to get down to what Simpson's rule did. So 100 million versus 100. 100 million times work, 100 times work. Trapezoidal rule would be in the middle. It would compromise, but it's still a vast difference between the two techniques. All right. So the left-hand rule assumed the function was constant. The trapezoidal rule assumed on each interval things were linear. The Simpson's rule assumed on pairs of intervals that we had a quadratic fit. What would be a natural thing to try next? All together. Cubic, exactly. And you can, and people do. It turns out that's not where the biggest payoff is, though, because this is simple and accurate enough for most purposes, sufficiently accurate. I would say it's the sweet spot between complexity and accuracy for most applications. To get to cubic, you get some complications with that. And one of the big complications is that you need 3 multiples of 3 intervals. Because they're going to fit a cubic, you need 4 points, which is 3 intervals. And nobody, for some reason, I don't know. Viscerally, I don't mind dividing my intervals into pairs. I'm OK with that. Dividing them into triples seems just kind of silly. Like, why would we do that? If there's no benefit, if there's no significant benefit. So Simpson's rule is what people use in practice for most data analysis, most integrals of this type. You'll see most tools based on that. What we're going to see is that the problem, the next problem, is not the accuracy, or it's not the accuracy on smooth functions. This function was really nice. It was very smooth. The problem is going to be discontinuities and other issues where making it a higher degree polynomial, we've seen this before, that makes it somehow smoother or somehow more complicated. That's not going to address the problem we're facing, which is the function does things like this, where no matter what I fit it with, a cubic, a quadratic, it's not going to be a great fit. It's just fundamentally different than what we're trying to fit it with. And so we're going to have to try some other approach. So for most, pretty much all vanilla, nice smooth functions, Simpson's rule will do the job. It'll do it well. It'll do it fast. We're going to see next class where that breaks down and how we're going to address that. Still using Simpson's rule, as it turns out, but tweaking it in a different way rather than going to more complicated schemes.